Good day, and thank you for listening to my presentation on effective quinclorac on wild oat fecundity and seed viability. My name is Eric Johnson, and I'm a research officer in the Crop Imaging and Agronomy Lab in the Department of Plant Sciences at the University of Saskatchewan. I'd like to acknowledge my co-authors, Professors Chris Willenberg and Steve Shirtliff, also from the University of Saskatchewan. So some background. Depending on the province, provincial surveys have found that up to 40% of the fields sampled contain multiple resistant wild oat that is resistant to both ACCAs and ALS inhibiting herbicides. These two groups are the primary sites of action used for wild oat control in Western Canada. Unpublished studies conducted in the 1990s in Western Canada on tame oat found that when quinclorac was applied to tame oat, it resulted in very little visual injury to vegetative growth. However, injury was visible during panicle emergence, and seed yield was reduced by as much as 80% in some cases. So with the decline of effective wild oat herbicides, the question we wanted to address was, could quinclorac application result in similar reductions in wild oat seed fecundity as it did in tame oat? Two studies were conducted in 2019 and 2020 near Saskatoon, Saskatchewan, Canada. Wild oat was seeded alone with no crop at 90 kilograms per hectare. The 2019 site also had a high inherent population of wild oat. Seeding dates were May 7th, 2019 and May 27th, 2020. We had a very dry spring in 2019 and the wild oat did not emerge until June 25th. Quinclorac was applied to wild oat at 125 grams active ingredient per hectare at the following growth stages: the 1 to 2 leaf stage, the 4 leaf stage, the 6 leaf stage, when the flag leaf was fully extended, or BBCH 41, and just at the beginning of panicle emergence, or BBCH 51. Merge adjuvant was also applied to the spray mix at 1% volume to volume. Treatments were applied with a backpack sprayer and applied in a carrier volume of 100 liters per hectare with a medium spray quality. Plot size was 2 by 6 meters. Treatments were arranged in a randomized complete block design with 4 replicates. Data collection included visual control ratings, biomass production, seed shatter by placing trays and plots at the beginning of seed shattering, seed yield, so the plots were harvested with a plot combine at crop maturity, seed 1,000 kernel weight, and seed germination. Non-germinated seeds were tested for viability with the crush test. Results. Quinclorac application resulted in minimal visual phytotoxicity during the vegetative growth stage, and it had no effect on wild oat biomass production. A delay in heading and maturity was noted with quinclorac applications. And you can see that in this photo. The wild oats on the left here that were from the non-treated checked have fully emerged from the flag leaf, whereas in the quinclorac application, the wild oat panicle is just beginning to emerge from the flag leaf. First, we'll take a look at the effect of quinclorac application on wild oat seed shatter. In 2019, application between the 4-leaf and flag leaf stage resulted in a significant reduction in wild oat seed shatter, whereas in 2020, application after the 6-leaf stage resulted in significant reductions. Overall, we saw up to a 68% reduction in seed shatter. So this could have some important implications for harvest weed seed control. The reduction in seed shatter could be partially explained by the delay in heading and maturity, but I also noted that the pedicel, this structure that attaches the spikelet to the rachis, was also thickened and distorted, and this may have had an effect on seed shattering as well. The effect of quinclorac on harvested seed yield. This is by weight and reported in grams per square meter. In 2019, seed yields declined when quinclorac was applied between the 4 and 6 leaf stage. In 2020, our yields were much lower due to lower emergence and lower inherent populations. However, application after the 6-leaf stage also resulted in lower seed yield compared to the non-treated check. Our best treatments resulted in up to a 57% reduction in seed yield. One thing that we noticed that the seed produced in some of the quinclorac treatments was visibly smaller than seed produced in the non-treated checks. In 2019, quinclorac application prior to panicle emergence resulted in lower 1,000 kernel weights. In 2020, application after the 4-leaf stage resulted in lower 1,000 kernel weights. Overall, we saw up to a 60% reduction in 1,000 kernel weight, which corresponds to the 57% reduction I noticed in yield in the previous graph. Thus, the reduction in seed yield is primarily due to the reduction in seed size. So if one calculates the number of seeds produced using the weight of the seed harvested and the 1,000 kernel weights, you will see that the number of seeds harvested were similar to the non-treated check in both years. So overall, quinclorac resulted in similar seed harvest numbers, however, they were just smaller. If we look at total seed production, so that's seed harvested and seed collected in the shattered trays, you will see that there was a slight reduction in total seed numbers produced with some of the quinclorac applications in 2019. In 2020, there was about a 50% reduction in total seeds produced when quinclorac was applied after the 6-leaf stage. Interestingly, with the high wild oat densities in 2019, there was only about 20% of the total seed produced that shattered prior to harvest, whereas 50 to 70% of the seed shattered prior to harvest in 2020. We next looked at the effect of quinclorac application on wild oat seed germination and viability. In 2019, about 70% of the seed germinated in the non-treated checks after 10 days. This dropped to 53% at the 1 to 2 leaf stage and below 5% at the 4 and 6 leaf stage. There was no difference in germination percentages when comparing application beyond the flag leaf stage and the non-treated check. About 30% of the seed in the non-treated check was considered dormant and viable based on a crush test. This dropped to 13% at the 1 to 2 leaf stage and less than 5% at the 4 and 6 leaf stage. Results for beyond the flag leaf stage were similar to the non-treated check. If we look at the percent of non-viable seeds, you can see that greater than 90% of the seed was considered non-viable when application was made at the 4 to 6 leaf stage. So keep in mind in 2019 that most of the effect occurred at the 4 to 6 leaf stage of application. Moving on to 2020, similar to 2019, About 70% of the seed germinated after 10 days in the non-treated checks. This dropped to 49% at the 1 to 2 leaf stage, 42% at the 4-leaf stage, and less than 5% when application was made beyond the 6-leaf stage. Again, the stages where quinclorac had major effects on reducing germination also resulted in high levels of non-viable seed. So remember, in 2019, most of the effect occurred at the 4 to 6 leaf stage, whereas in 2020, most of the effect occurred beyond the 6 leaf stage. So you can see the visual effect of quinclorac on the wild oat seed is that it's smaller, well, actually thinner. And this photo actually illustrates it better. Some of the seed from the quinclorac application is just basically the seed coat with small amounts of endosperm. Preliminary conclusions. Quinclorac application in wild oat had no effect on vegetative growth but delayed crop development. Reduced seed chattering by up to 68%. Reduced seed yield by up to 57% due to a similar reduction in thousand seed weight. Reduced seed germination and viability by greater than 90%. Effective application timing was inconsistent between years. However, results were consistent at the 6th leaf stage in both years. Some concluding remarks. In Western Canada, quinclorac is primarily used in cereals and canola for control of false cleavers. Would growers use it for wild oat if the only effect was to reduce seed return, or would they just consider it as a side benefit if they applied it for cleavers control? Future research, we only investigated the highest registered rate, and many growers use a lower rate for cleavers control, so we are unsure what effect this lower rate could have on wild oat seed return. I'd like to finish by acknowledging the technical support of Sean Campbell and Cindy Redicott, and the financial support of both the Government of Saskatchewan and the Government of Canada, as well as the Saskatchewan Wheat Development Commission and the Alberta Wheat Commission. Thank you for listening.